Good morning. In our previous session, we have discussed about potentiometric estimation or potentiometry. In potentiometry, we are going to estimate redox reactions using or measuring potential. So there, we are going to use two electrodes, that is, one is indicator electrode and other one is standard reference electrode. So by measuring the potential of the reaction, we can estimate or determine how much amount of the titrant is required to oxidize or to reduce the sample present in the beaker. So now we are going to discuss about conductometry. So the acid-base reactions whichever we do in a classical method can be determined or estimated by measuring the conductance of the reaction. So what do you understand by conductance? The first thing, as soon as we tell the term conductance, the first thing which comes to our mind is the conductors. So what are conductors? Any substance which allow electrons to flow through it, or in general current to flow through it, is called as conductor. Since these are experiments, so conductance means it is a property of a substance to allow the ions or the charges to flow through it. But here we are dealing with reactions. So what do you mean by reaction? What do you mean by conductance with respect to reactions? We'll discuss that. So in conductometric estimations, the basic principle is Ohm's law. So what is Ohm's law? All of you know very well, very well versed with Ohm's law because you've studied it in your electrical, right? So Ohm's law, it states that, or it is according to Ohm's law, the current flowing in the conductor is directly proportional to the applied EMF. So that is I is directly proportional to E. So that is I is equal to ER. So it is ER, where R is the proportionality constant. So R is nothing but resistance. R is nothing but resistance offered by the conductor. Okay. So let us see what is conductance in terms with respect to solution and reaction. So conductance is directly proportional to the various conductance directly proportional to the mobility of ions. Conductance depends upon temperature, concentration of ions, and types of ions present, that is cations, anions, whether it is singly or doubly charged, etc. So mobility. So conductor is if it is a solid. So if the conductance means it is the capacity of the substance to allow the charges to flow through it. But in terms of solution or a reaction, so reaction occurs only in what? Liquid state here, right? Solution state here. So what is conductance here? So it is mobility. Mobility means movement of ions. So each and every ion will move in a different speed. So conductance is directly proportional to mobility of ions. So various factors whichever depends, where conductance depends, mobility plays a very, very important role. So conductance is directly proportional to mobility of ions, and conductance depends upon concentration of higher mobile ion. If the concentration of, you might have n number of ions, you might have H plus ions, you might have Na plus ions, you might have Cl minus ions. So whichever concentration mobility of the ion is more, conductance depends upon that particular ion. For instance, if you have H plus, Na plus, Cl minus, the mobility of H plus is high. So therefore conductance depends upon concentration of H plus ion. So if the concentration of H plus ion is higher, then conductance also will be high. If the concentration of H plus ion is low, conductance is also low. For instance, let us consider we have a running competition. We are allowing 110 people to run. So Olympics, right? So how many will get gold medal? 1. How many will get silver medal? 2. So very rare cases, 3 of them will share the bronze medal, right? So similarly, we have n number of ions, right? N number of cations, n number of anions. So each and every ion have a unique mobility, and so depending upon the mobility, the conductance also will vary. It is conductance is directly proportional to mobility. So if the mobility is high, conductance is high. So conductance depends upon concentration of the higher mobile ion. If the higher mobile ion concentration is high, then conductance will be high. If the concentration of higher mobile ion is low, then conductance is also low. So these are the three factors which are supposed to remember. So why? We'll see that later. So where are these conductometric estimations are used? These conductometric estimations are used to determine the endpoints of acid-base reactions. So acid-base reactions are usually called as neutralization reactions. So it also used to determine the endpoint for displacement reactions, precipitation reactions, etc. So after performing the experiments, you're going to plot the curve. By plotting the curve, you're going to determine the endpoint. So what are the requirements for this conductometric estimation? So what is the conductivity cell? We'll see. So for the, you need a titre, you need a burette. So you need a sample holder, that is a conical, instead of conical flask, you're going to use a beaker, okay, in which sample will be taken. So you're going to add a magnetic stirrer, or you can use a blowpipe to blow. Instead of stirring each and every time, after adding a titrant, you can add a magnetic stirrer and a conductivity cell. So conductivity cell here, it is made up of two platinized foils. You will have two platinized foils, so which are sealed glass, sealed, and the distance between these two platinized foil is 1 centimeter area, and the surface area of this platinized foil is also 1 square centimeter. Okay, so it is 1 unit area, and distance is also 1 centimeter. So whatever conductance is measured between these platinum foils is called as specific conductance. So you're going to measure specific conductance here. So the conductivity cell will be dipped into the solution of which the conductance should be measured, and it will be connected to the conductivity meter. So in order to stir, you're going to add magnetic stirrer. If there is no magnetic stirrer, you can take a blowpipe and you can blow it. So in order to avoid, if you stir, what will happen? The either platinum electrode may get platinum, that is conductivity cell may get damaged, or you may end up in breaking the beaker. So in order to avoid that, you're going to add magnetic stirrer or a blowpipe. So let us see where it is mainly applied. So it is mainly applied, as we have discussed, in acid-base reactions. Acid-base reactions, we have n number of acid-base reactions. That is, the first one to start with, strong acid with versus strong base. So what is strong acid? HCl. What is strong base? NaOH. So acid-base reactions, usually the product is salt and water. When NaOH reacts with HCl, we get NaCl and water. So we're going to take NaOH in the burette, it is strong base. We're going to take HCl in the beaker, dip the conductivity cell, and add NaOH in the increments of 0.5 ml. When you add NaOH in the increments of 0.5 ml, the conductance starts decreasing. Why? Because initially the beaker contains only HCl. So HCl means H plus and Cl minus. HCl is a strong acid. It ionizes completely to give H plus and Cl minus. So the mobility of H plus is very high compared to Cl minus. Therefore, conductance depends upon the concentration of H plus ion, because the higher the conductance, higher the mobility, higher will be the conductance, right? So high, and other thing is, conductance will always depend upon concentration of higher mobile ion. If the concentration is high, conductance also will be high. If the concentration is less, conductance also will be less. So before adding NaOH, the concentration of H plus ions in the beaker is very high. So therefore, the conductance will be high. When you add NaOH from the burette to the beaker, the conductance starts decreasing because the H plus ion concentration decreases. The H plus gets converted to water as shown in the reaction. So from 100 it will become 90, 90 to 95, 90 to 80, 70, 60, 50, and gradually it will become 0. So once it becomes 0, when you add NaOH, because there is no change in color, right? Only you're supposed to know with respect to conductance. When entire HCl gets neutralized, you're going to add NaOH. When you add NaOH, extra add NaOH remains in the beaker as Na plus and OH minus. Now conductance starts depending on OH minus ion, because mobility of OH minus ion is higher compared to Na plus. As concentration of OH minus ion increases in the beaker, the conductance also will increase. So going to take another 5 or 6 readings, you're going to stop the experiment. we're going to plot a graph of conductance versus volume of NaOH added as shown in the graph. We're going to get two curves, a V shape. So from the point of intersection, we're going to drop a perpendicular to x-axis that gives the volume of NaOH required to utilize the HCl or utilization point. This is one. So next we have strong acid versus weak base. So strong acid, H2SO4 we're going to take in the burette, and weak acid, it might be acetic acid or any organic acids, or you're going to take ammonium hydroxide, can take in the beaker. So we're going to dip the conductivity cell as usual like previous experiment. Going to add the acid in the increments of 0.5 ml. So when you add in the increments of 0.5 ml, we're going to take ammonia in the burette and we're going to take acid in the beaker. So as you add ammonia, as you go on adding, what will happen? The H plus starts neutralizing. So when the H plus starts neutralizing, what will happen? The H plus starts neutralizing means the concentration of H plus will decrease. As the concentration of H plus decreases, the conductance also will decrease. You can see the fall of conductance, decrease of conductance in the curve. So later, the extra added NH4OH, ammonium hydroxide, will split to give you NH4 plus and OH minus ion. So this NH4 ammonia will not completely ionize because it is a weak acid. It will partially dissociate. Since it will partially dissociate, there will no change in conductance, and the conductance will remain constant. So there is no OH minus ion, there is no, what will happen? NH4 plus and OH minus ion. So NH4 plus and OH minus ion, since it is partial dissociation, the concentration of both are equal. So NH4 plus NH4OH gives NH4 plus, that is, it will be in equilibrium. So since it is in equilibrium, there is no change, therefore it is constant. We get a L-shaped graph. So at the point of intersection, we are going to drop a perpendicular to the x-axis. So that gives volume of NaOH required to utilize the sulfuric acid present in the given solution. So next, so we're going to take mixture of acid versus strong base. So mixture of acids. So if you want to neutralize mixture of acids using classical method, you can do it. So for that, you are supposed to use two different indicators. You cannot add two different indicators at the same time. So if you have a mixture of acids by volumetric method, supposed to do methyl orange other indicator, but you cannot do at a time because these two indicators can mutually interact with each other, or this may interfere in the reaction. So what you're supposed to do is, first you're supposed to neutralize one, first you're supposed to add one indicator. For example, if you're taking two strong acids, HCl and sulfuric acid, for sulfuric acid separate indicator, for HCl separate indicator. Once entire H2SO4 is neutralized, then you're supposed to add another indicator for HCl for other reaction. So therefore it is a difficult process. So it may react with the acid, the indicator may react with the acid, or mutual reaction may also occur. But here in conductometric estimation is a very, very big advantage here. So both the acids can be estimated easily. So mixture of acids, it will be two strong acids, two weak acids, one strong acid, one weak acid will be taken and will be estimated against the strong base. So here, for example, you have taken HCl and acetic acid and titrated against NaOH. So NaOH is taken again in burette and acetic acid and mixture of HCl is taken in the beaker. You are going to dip the conductivity cell and add NaOH in the increments of 0.5 ml. So always when two acids are there, always stronger acid will get neutralized first, later the weaker acid. So since HCl is a stronger acid, HCl starts getting neutralized. Since H plus ion concentration decreases, conductance also will decrease. Later, acetic acid starts neutralizing. Once both the acids neutralizes, so what will happen? Extra NaOH remains in the beaker as Na plus and OH minus ions. So now the conductance depends upon OH minus ion. So as the concentration of OH minus ion increases in the beaker, the conductance also will increase. So we're going to take another 4 or 5 readings and stop the experiment. So initially conductance decrease, later slow increase, later there will be a rapid increase. When the conductance increases rapidly, we're going to take another 4 or 5 readings and stop the experiment and plot a graph of conductance versus volume of NaOH. So you get 3 curves. So we're going to extrapolate the curves so that the 3 curves will intersect each other. So the first point of intersection are going to draw a perpendicular to the x-axis and it called as V1. So other point you're going to call it as V2. So V1 gives you volume of NaOH required to neutralize HCl. V2 gives you total volume of NaOH required to neutralize both the acids. Whereas V2 minus V1 gives you the volume of NaOH required to neutralize only acetic acid. So similarly, we can find out endpoint for weak acid versus weak base, weak acid versus strong acid. So strong acid similarly for so many uneven displacement reactions also. I've just taken 2 or 3 examples. So for most of the reactions, endpoints can be done. So major advantage of this is mixture of acids can be estimated accurately. So thank you.